Welcome to Limits and Continuity, an informative video made by Kayleigh and Imelda de la Rosa. So it's been a while since we've gone over limits and continuity since we did this back during the first 6 weeks. So hopefully this video can be a little refresher on what both of these are. So first we are going to start off with limits. And so basically the definition of a limit is the value that a function approaches. So for example, if you take a look at this graph, you can see that f of x, this pink line here, as the x value increases, the y value gets closer and closer to 0. So in this case, our limit would be 0. And now whenever we take limits, there are two ways we normally see them show up. So you can either have to take a limit as x approaches a number, or as a limit as x approaches infinity. So the first thing we're going to go over with limits is what you do if in the problem you're solving, you're supposed to find out the limit of x approaching a certain number. So your first step, what you're going to do is you're going to plug that number in. And if you plug that number into the problem and you get an actual numerical answer, then that is your limit. But let's say you get 0 over 0, or for any reason your denominator is 0, then you're going to have to take this a step further. So if you get undefined as your answer after doing step 1, you either need to factor, multiply by the conjugate, do a trig identity, or simplify. And Imelda will show you a few practice problems on how to approach this.
So our first example will be to find the limit of 3x plus 5 as x approaches 5. So in this case, all we have to do is just plug it into the equation. So then we get 3 times 5, which is 15, plus 5, which equals 20. And that is our limit. Okay, so our next example would be to find the limit as x approaches 5 in this function, x squared minus 25 over x minus 5. So in this case, if we were to plug in, we'd get 0 over 0, and that's not mathematically correct. So what we would have to do is factor the top using algebra, and we would get x plus 5 and x minus 5 all over x minus 5. So now we can cancel out the x minus 5's. So then we have the limit of x plus 5 as x approaches 5. And then all we have to do is just plug in to get 5 plus 5, which is 10. And that's your limit. Okay, for our last example, we have root x minus 3 over x minus 9. So to find the limit of as x approaches 9, we have to multiply it by 1 because we can't factor, so we're going to be rationalizing. So when we multiply it by 1, we're going to do it a bit differently. So it'll be root x plus 3 over root x plus 3. So we have to distribute the top, and as we're distributing the top, we'll notice that the roots cancel out to get just x, and then the 3 root x's will also cancel out, and then it'll just leave us with x minus 9 over x minus 9 times root x plus 3. Notice how I didn't distribute. This is because it's easy to cancel out, so we'll just cancel out x minus 9's. So now it'll be the limit of 1 over root x plus 3. And in that case, we'll just plug in, which will be 1 over root 9 plus 3, which will be 1 over 3 plus 3, which equals 1 over 6. And that's your limit.
Now, on to how to solve problems that ask you to find the limit of x to infinity. So first, whenever you see the limit of x to infinity, you need to keep in mind that here you're going to try to look for a horizontal asymptote. And in this case, you can sort of think of the idea that your horizontal asymptote will equal your limit. And whenever you're trying to find a horizontal asymptote, you need to look for your coefficients. We're also going to look at the degree. So let's start off with our first example. So what happens if on your equation, such as this one, you have the same leading degree in both your numerator and denominator. So as you can see here, on our numerator we have 5x to the 8th and we have 6x to the 8th. So basically our degrees are the same on both the top and bottom. So to solve that, what we're going to do is we're going to take the coefficient of the highest degrees on the top and bottom, and we are going to divide them. So let me just take out my marker and mark this. So since we have our highest degrees are both 8, you're going to single out this 5 and you're going to single out this 6 and divide them, and your answer here is going to be 5, 6. However, what happens if the degree of your numerator is bigger than the degree of your denominator? If that happens, that means that you're going to have no horizontal asymptote. So in this problem down here, you can see that the highest degree in our numerator is 8, and the highest degree of our denominator is 3. And so since the top is bigger than the bottom, we are going to have no horizontal asymptote. And then, if the degree of our numerator is less than the degree of our denominator, then our horizontal asymptote is going to equal 0. So in this problem, you can see that the highest degree of our numerator is to the 8th power, and the highest degree of our denominator is to the 10th power. Then since the bottom is bigger than the top, our horizontal asymptote is going to be 0. It's also good to keep in mind that you are also able to solve your limits graphically. So, for example, let's take a look at this graph. In this case, you can see f of x, which is our pink line, is going towards infinity, but what we're trying to figure out here is what is the limit when x approaches 2. So as you can see, as where x is 2, our limit is going to be 3. And so this is an easy question to answer. But let's take a look at a graph where you have a vertical asymptote. So as you can see here, as f of x approaches 2, it never actually hits 2, it just keeps on going to infinity. Or at least your y value keeps on going to infinity. So your limit here would be as x approaches 2, your limit is infinity. And then what happens if you have a horizontal asymptote? So basically, even though there's a hole here at x equals 2, that's okay, because both the left side of your line and both the right side of your line, or of f of x, both meet in the same place, which means that your limit here is 4, even though technically there's not an actual point there. So that is limit, and now we're going to move on to continuity. So basically, the idea of continuity is that there are no interruptions in the graph. And by no interruptions in the graph, that means there are no holes, no vertical asymptotes, no jumps, no gaps, and no breaks at the point of the graph that you're looking at. So in order for a function to be continuous, it has to follow 3 rules. So the first rule is that f of c is defined. The second rule is that the limit as x approaches c exists. And the third rule is the limit as x approaches c equals f of c. So for the third rule, basically that means whatever answer you get for number 1 equals whatever answer you get for number 2. And this is easier explained with the graph. So let's take a look at this graph here. And the point we're going to be focusing in on this graph and all the other graphs is our limit as x approaches 2, and we're going to find out if it's continuous or not. So we have to make sure that it meets all the 3 steps. So first, we need to see that is f of c defined. So our c here equals 2. So as we can see, our x of 2 is defined. Yes, so let's say, I didn't put a number there, but let's say that equals 1. So our f of c equals 1, that's good, it's defined. We can move on to the second step. So the second step is as the limit as x approaches c exists. So does the left side of our graph meet the right side of our graph? Yes, it does. And where does it meet it at? Where y equals 1. So that means yes, number 2 also works. So we have to check. Does the limit as x approaches c equals f of c? So does our answer that we got for number 1 equal number 2? Yes, it does. And so that means that this function is continuous. Now let's look on to a different graph. So at this graph you can see that we have a vertical asymptote at x equals 2. So let's take a look at our first rule for continuity. F of c is defined. So as in the previous graph, c here is 2. So since there's a horizontal asymptote on 2, it's not defined, meaning that this graph is not continuous. And now we're going to take a look at a third graph. So we're still going to be looking at f over c and if that equals, and with c being equal to 2. So f over c here, or f of c here, we can see that f of c equals 5. So that's good. We have a value for that, and we're going to go on to the next step. So the limit as x approaches c exists. So as x approaches 2, we can see that yes, there's a limit, and that limit is right here, 3. And now we're going to look at our third rule. So basically, does what we got for number 1 equal what we got for number 2? So for number 1, we got our limit as, or f of c as 5, and for number 2, we got our limit as 3, so those do not equal, meaning that this graph is not continuous. So finally, we're going to take a look at one more graph right here. So let's see, is f of c defined? Yes, we can see f of c is defined up here. I didn't put a number up here, but let's say that equals 4. So yes, f of c is defined. Now let's take a look at our next rule. The limit as x approaches c here, as we can see, the left side of the line does not match up with the right side of the line, so there is no limit, meaning we can't fulfill rule number 2, meaning that this is not continuous. And so whenever you're trying to solve continuity algebraically, or not algebraically, but like when you have an actual problem in front of you, you have to figure out, are there any holes, are there any vertical asymptotes, and are there any breaks or jumps? So here's just a little example problem. So in this problem here, it's sort of asking us, is this continuous? So we have to look for holes. Are there any holes? We can see here that x minus 3 over x minus 3 cancels out here, which means that yes, we do have a hole at x equals 3. But we can also go on to look at our vertical asymptotes, and we can see here that we have on the denominator x plus 1, which means yes, we're going to have a vertical asymptote at x equals -1. And so since yes, we have holes and vertical asymptotes in this equation, we can say that no, this equation is not continuous. And so that is all we have for you today about limits and continuity, and hopefully that helped.